Let's talk about the messy world of polls and election predictions. Polls are an important tool that statisticians and econometricians use to gauge support for different candidates before an election. How do polls work? And how do you know which polls you can trust? Welcome to another episode of Planet Econ. Even in the perfect theoretical world, polls don't work nearly as well as you might think. A poll is supposed to work like this. First, you gather a random sample of voters so that the people in your sample are representative of the whole population of voters. Then, you ask the people in this random sample which candidate they will vote for. The number of people that you obtain an answer from is the sample size of your poll. After that, you turn each person's original response into a dummy variable, which is the name that econometricians gave to variables that can only take on a 0 or a 1 as its value. And obviously, dummy variables are not dumb at all. Not sure why they came up with this name. Anyway, back to what I was saying. How does this conversion of responses into dummy variables work exactly? Say the question in your poll had the options Kamala Harris, Donald Trump, and a candidate other than Harris and Trump. You would create a dummy variable called Harris that only equals 1 if a sample person responded that they will vote for Harris and equals 0 for everyone who answered something else. You would also create a dummy variable called Trump that only equals 1 if a sample person responded Trump but equals 0 for all other respondents. And you would create a third dummy variable called Others that equals 1 if a person answered that they will vote for another candidate. After you've done that, it is time to count how many ones you've got for each dummy variable and divide this number by the total number of people in your sample. Doing this gives you a sample average, or sample mean. So, for example, if you got 51.1% for the sample mean of the variable Harris, it means that 51.1% of the people in your sample intend to vote for Harris today, assuming that everyone responded honestly. Now, here's where things get a little weird. After all, we don't really care about what things are like in one specific sample. A poll is trying to get at what proportion of people would vote for a candidate when the whole population containing all voters is considered. And the only reason that a poll doesn't survey the entire population is doing that would probably make a pollster broke. So, we really care about the population mean, which is what we would get if we actually did ask every single voter there is, turned their responses into dummy variables, and calculated the means of those dummy variables. However, even in the theoretical world, presuming that you have followed all of the above steps absolutely perfectly, and you were too broke to poll the entire population, the probability that the sample mean you get from your poll will end up equaling the population mean is 0. Yes, you heard that right. Even in the theoretical world, where sample means will never equal the true levels of support these candidates have when all voters are considered. So if you got a sample mean of 51.1% for Harris, with all zeros in the decimal places after these 3 digits, you actually know for sure that the true level of support for Kamala Harris is not equal to this number. This is because a candidate's true level of support in the population can be any rational number between 0 and 1, or 100%, with decimal digits as crazy as there can be, and calculating the sample mean is kind of like throwing a zero-width dart at the continuous and infinite rational number line between 0 and 1, and hoping to hit a specific point. You can get close, but as long as you zoom in enough, you will always miss. So how come we still care about the sample mean from polls? It is because we can count on it being close to the population mean most of the time. Perhaps you have heard of this thing called the law of large numbers. Perhaps you have also heard the assertion that the law of large numbers guarantees that the sample mean will always be close to the true population mean, as long as your sample size is large enough, and you followed all the steps mentioned earlier in the video perfectly. The truth is a little bit less straightforward and slightly disappointing. Here is the extremely convoluted idea that is actually expressed by the law of large numbers. Step 1. Define your personal threshold of the sample mean being crazily far away from the true population mean. you can dictate that if the sample mean your poll got was off by more than 17 percentage points from the unknown true population mean, then it is crazily far away. Or you can dictate that if the sample mean you got was off by more than 0.0001 percentage points, then it can be classed as being crazily far away. In this step, you can be as stringent or lenient as you like. Just don't choose 0 as your threshold, because we already went over why you will never hit the exact population mean. Step 2. The law of large numbers comes in, comforts you, and tells you, don't worry, whatever threshold you chose in step 1, I guarantee that as the sample size of your poll gets larger and larger, the chances that you will get a sample mean that is crazily far away from the true population mean will get smaller and smaller. This really does apply to all thresholds that are not 0. Step 3. The law of large numbers reveals that he is actually somewhat of a supervillain and informs you that no matter how large your sample size is, as long as you did not poll the entire population, there is always a small chance that your sample mean is actually crazily far away, and this chance never drops to 0. Just to amp up the tension a bit more, the law of large numbers adds in a slightly sinister voice, no matter how many samples you draw, you will never find out for sure if you were close enough to the truth. Never! So, even in a perfect theoretical world, the best you can hope for is that if it has a sample size that is large enough, then it will probably give you a number that is not crazily far away from the true level of support that a candidate has among voters. But it is not completely guaranteed. If this section of the video sounded really confusing to you, don't worry. This is actually PhD level stuff. Or maybe you've managed to follow along during the entire section. If so, congratulations! You have just unlocked a very advanced concept of convergence and probability. When it is not feeling so mischievous, the law of large numbers actually presents itself thus. If random sampling is used, then the sample mean converges in probability to the true population mean. This is just the formal wording of the idea that we have explored together in this part of the video. Remember that up to now, we have been staying in the perfect theoretical world. The problems we have been talking about become minuscule in size when we jumped into the real world. No, you will never find out if your sample mean is in fact far away from the true population mean, but with very large sample sizes, the probability of that happening becomes very, very small in the theoretical world. In the real world, however, it is pretty hard to even sample people randomly. For example, since most voters in the US have a cell phone, a pollster might start out with a list that contains the cell phone numbers of every single eligible voter in a state and randomly select a set number of cell phone numbers from this list. This step is super easy to achieve with the help of some basic coding. However, once the pollster starts calling the numbers on the smaller list, they cannot force people to answer their phones and not hang up before they finish answering the poll's questions. Thus, you might imagine how someone who works 3 jobs and is raising kids might be much less likely to respond to the poll than someone who has no kids and is just working 1 very light job. Random sampling requires that people only enter your sample through sheer dumb luck. So only getting answers from people who have more time on their hands violates random sampling. As an attempt to address this problem, after asking you whom you will vote for, pollsters ask you additional questions about yourself. Basically so they can go like, hey, we managed to get 1 person who works 3 jobs and has kids to respond to our poll. Since there are many voters out there who work 3 jobs and have kids, let's pretend that this 1 person who responded is several people and count them many times. Obviously, it is very unlikely that this 1 person would be able to represent the political opinions of everybody who works 3 jobs and has kids. Maybe this person responded because their 3 jobs are economics professor, researcher for a tech company, and editor of an economics journal. And that's why they're very keen to respond to polls. This person probably has very different political views from someone who, say, works 3 customer service jobs. Once you take away random sampling, what you get from your poll does not even converge in probability to the true level of support a candidate has in the whole population. Another problem that pollsters face in the real world is that people may respond dishonestly. Before the 2016 election, most polls did not indicate a Trump victory. One potential reason for this inaccuracy is voters who intended to vote for Trump may have been afraid of facing negative social consequences if they indicated in a poll that they would vote for Trump. The second source of inaccuracy may also affect the polls for this election, given that Trump is running again. Another point is that polls are about how things are like for each candidate at the time the poll was conducted. They're snapshots of the present as opposed to the future, in which the election will take place. So polls can also falsely predict that a candidate will win if many voters change their minds between the time they were polled and the election. A rather sophisticated term that you may have seen thrown around in polls is margin of error. What is a margin of error and how do pollsters calculate it? To address these questions, we need to head back into the perfect theoretical world for a moment. Remember the estimate for the sample mean got above? That should technically be called the point estimate of the sample mean. If you take that number that you got for the point estimate of the sample mean and subtract the margin of error from it, you get the lower bound of your confidence interval. And if you take that number and add the margin of error to it, you get the upper bound of your confidence interval. It turns out it is not possible to calculate a margin of error without choosing a level of confidence first. If your level of confidence is 95%, which is the usual standard choice, by the way, then it means that with 95% probability, the confidence interval you constructed using the margin of error and the point estimate for its sample mean will contain the true population mean if one condition is met. What is this one condition? That you have an infinite number of people in your sample. You see, confidence intervals are calculated using the normal distribution, which is the bell curve that looks like this. And with dummy variables, you don't get the normal distribution unless the number of people in your sample is infinity. There aren't even an infinite number of people on this earth, so obviously, pollsters are unable to meet this condition in real life. For this reason, even if a pollster somehow pulled off random sampling perfectly, and everybody responded honestly to the questions on the poll, you should only interpret the confidence interval constructed using the margin of error as something that contains the true level of support for a candidate approximately 95% of the time. Because with large sample sizes, the distribution would be approximately a normal distribution. Now, when I learned this stuff for the first time, a question popped up in my head. Why not choose an 100% level of confidence? This way, you will know for sure that the true level of support that a candidate has will be in her confidence interval. The reason we can't choose 100% is the normal distribution has mass from negative infinity all the way to positive infinity. So if you constructed an 100% confidence interval, it would have negative infinity as its lower bound and positive infinity as its upper bound. It would be like saying, we know the true level of support a candidate has is somewhere between negative infinity and positive infinity. That is effectively saying nothing. So we have a trade-off between the amount of information we can express and the level of certainty with which we can express that information. Now, as usual, things get even messier when you take it into the real world. It may feel really nice to have a range that contains the truth with approximately 95% probability, but with election polls, especially those conducted in battleground states, the confidence interval often contains 50%, so it doesn't tell you which candidate would win the state. Thus, it really is very, very difficult for polls to get an accurate picture of the true level of support that a candidate has. With the Electoral College, it is also very hard for pollsters to predict the outcome of a specific election, because the candidate that wins the most number of Electoral College votes wins the election. The number of Electoral College votes that a state has is equal to the number of congressional districts that the state has plus 2. So it is not proportional to population. In all states except for Maine and Nebraska, The candidate that receives the most number of votes in the state gets all of the electoral college votes of the state. And in Maine and Nebraska, electoral college votes are allocated to the winner of each congressional district, and the remaining electoral college votes are allocated to the overall winner of the state. Thus, under the electoral college, the candidate who wins the battleground states wins the election. So you should pay special attention to polls in battleground states rather than national polls. Just one final note on polls. So far, we have only been talking about polls in which voters are asked about which candidate they will vote for. These are opinion polls. There are also prediction polls that ask sampled individuals not which candidate they will vote for, but which candidate they think will win the election. Those polls have many similarities with opinion polls, and many of the points in this video apply to prediction polls as well. So which polls should you trust more than others? The answer is polls with large sample sizes and polls who come the closest to conducting random sampling. I believe that many pollsters try very hard to get an accurate picture of the whole population, but given that they face many theoretical and practical problems, it may be worth it to take some time to read the fine print the next time you encounter a poll. If you enjoyed this episode, please like, subscribe, and consider supporting Planet Econ on Patreon. Stay inquisitive, and see you next time